Hello and welcome. I'm Professor Sean Tavalia, Academic Chair for Physical Science at Suffolk County Community College and founding member of the board of Hamptons Observatory. For those not familiar with our organizations, the Hamptons Observatory was founded nearly 20 years ago with a mission to promote an understanding of and an appreciation for science through free quality education programs and access to astronomical observatory facilities. Tonight's event is co-sponsored by the Suffolk County Community College's National Science Foundation-sponsored iSuccess program, a program that provides scholarships and extracurricular activities for students enrolled in STEM fields. Although this event is free, it could not be possible without the generous donations of people like you. For more information on how you can donate to ensure these programs continue, please visit the Hamptons Observatory website. If tonight's presentation inspires you to learn more, please consider enrolling in one of the many traditional or online astronomy courses or chemistry courses offered at Suffolk County Community College. Tonight's speaker specializes in developing light pulse atom interferometers and optical atomic clocks and their applications to both fundamental and applied physics in space. He currently serves as project scientist and a principal investigator for NASA's Cold Atom Lab, a multi-user facility operating on board the International Space Station, dedicated to the study of quantum gases in space. He has been awarded both the prestigious Lou Allen Award for Excellence and the NASA Honor Award, Early Career Public Achievement Medal for significant early career contributions to his field. Dr. Williams received his PhD from Penn State University, studying ultra-cold Fermi gases. He previously held an NIST NRC postdoctoral research associate in Professor Jun Yi's lab at the Joint Institute for Laboratory Astrophysics and the University of Colorado, where he developed high-precision optical lattice clocks. And with that, please join me in welcoming Dr. Jason Williams. Jason.
All right. Well, thank you, Sean. I appreciate you inviting me, and also to Donna for inviting me to speak to you tonight. As Sean said, I'm going to talk to you about NASA's Cold Atom Lab, 6 years of quantum research that we've been studying on the International Space Station. I just want to start by mentioning that this multi-user facility is funded by NASA, specifically the Biological and Physical Sciences Division of NASA's Science Mission Directorate, in collaboration with the ISS Program Office. So I'll start with just a brief, little bit more about me from what you heard from my bio. I was born and raised in Idaho. That's where I actually went to school to get my undergraduate degree at Idaho State University, where I studied high energy physics, actually, particle accelerators, creating positrons and which are the antimatter to electrons, to study material science. But right around when I was graduating from the undergraduate, some very interesting results were coming out in the world of atomic, molecular, and optical physics that some of these that I'll talk to you about in the future. So I booked it over to Pennsylvania, did my graduate work there, studying ultra-cold gases, and then from there went to Colorado to work at JILA, this Joint Institute, with Juni's group, and there studied precise clocks called optical clocks, which use an optical transition, where we achieved record performance in both frequency, stability, and accuracy at the time. Now, when we're talking about accurate clocks, these can measure the second with 18-digit points. So over the lifetime of the universe, a clock would be accurate to within about a second. And then from JILA, I went to Jet Propulsion Lab in California. And there I've been involved in Cold Atom Lab, project scientist for one of the for the mission. I'm one of the investigators, but I've also worked on some optical clock projects. And I want to show in the lower right corner, that's me and one of my sons at one of the launches that occurred in Wallops, and this has been a really great experience. We've been able to not only work with instruments on the ISS, but see hardware go up, and it's been a great experience working with NASA. Working at Jet Propulsion Lab. For those of you that don't know, this is Jet Propulsion Lab is a FFRDC, federally funded research and development center, managed by NASA, but we actually work for Caltech. And it's developed for the focus on robotic exploration of the solar system. So some of the notable firsts for JPL, it's been around for a long, long time. We had America's first Earth orbiting science satellite, Explorer 1 in 58. It has been critical to all of the Mars orbiters, and the rover program is led there. We actually just had a launch of Europa Clipper yesterday that went successful. That in about 5.5 years is going to do close flybys of Europa to look for the conditions on that moon of Jupiter, and had over 144 missions to date. We also manage the Deep Space Network, which still talks to Voyager satellites that are still surviving after their launch in 1977 and are the only spacecraft to enter interstellar space. So we have quite a few missions, but today I'm going to talk about one of the first missions that studies quantum physics in space. Specifically, we're studying a unique fifth state of matter called a Bose-Einstein condensate. I'll explain that to you a little bit more, and how quantum matter can be studied in space, and it can actually be used for some precise sensors in the future. So I'll talk very quickly about some of the quantum ideas that we're interested in utilizing in the Cold Atom Lab, and then a review of the research that we're doing and some anticipated impacts from our research. We work for the fundamental physics program in BPS, so we're able to study some of the big questions, and that's really one of the great things I must say about my job. So first, I'll start with a 2-minute quantum interview or quantum overview. Quantum mechanics, really at its heart, says that matter can act as waves. And so to understand waves, I mean, you've probably seen them, these most in relation to water. You disturb water, you get this repeating pattern of peaks and valleys, and the periodicity of when that pattern repeats itself is called the wavelength. You also probably know that when two waves come together, if they're so-called in phase, where the peaks line up, they can have constructive interference, make a bigger wave. When they're out of phase, when peaks line up with valleys, you can get cancellation, destructive interference. And even going to 2 dimensions, you can have some pretty complicated interference patterns that can emerge, such as with these 2 fishermen that are interfering with each other as they're trying to catch some fish. Light also acts as a wave. This was, you can see from Young's double slit experiment, where beam of light sent through 2 slits. Each slit acts as sort of a source, sort of like where the pond was disturbed by the bait of the fisherman. And these 2 waves propagate out so that when they hit a screen, you can see this pattern of light, dark, light, dark, light, dark, light, dark. That's an interference pattern of that you can see from light. And from that, it's very strong evidence that light acts as waves, to the most part. What about matter, though? Matter has a so-called wave-particle duality. And so if I take electrons from electron gun, send them through a double slit one at a time, and they hit a screen, they're going to hit the screen in a certain spot, showing like a particle does, right? But the interesting thing is that if I take electrons and keep throwing them through the slit one at a time, pop, 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 they'll hit the slit like particles, but they can actually build up an interference pattern of this light, dark, light, dark, light, dark. And the interesting thing there is that means that the electrons had to act as waves going through the slits. Each electron had to actually go through both slits at the same time, come out on the other side, either constructively or destructively interfere with itself to make this pattern. And that is sort of the wave-particle duality of matter. The matter can act as waves in certain phenomena, it can act as particles, and it depends on properties and when it's being measurement, what properties you see from the matter. This wave-like nature of matter can have very impactful, or it can be very impactful even to our everyday lives. One phenomena is called tunneling that you do not get with classical matter. And this is, if I take a ball and I throw it against a wall, billions upon gajillions of times, there is a finite probability that that ball will actually tunnel through the wall and end up on the other side. And the reason for this is because that ball has a wave-like nature. A little bit of that wave extends beyond the wall itself. And so you can have a finite probability that when you measure where the ball is, it'll be on the other side of the wall. This never happens in the classical world that we live in with balls and planets and people. It just doesn't happen. But when you look at atoms and subatomic particles, this is a critical part of our life. And this is actually one of the critical ways that our sun works. To have two hydrogen atoms fuse into a helium atom, in general, they don't have enough energy in the sun to overcome the Coulomb repulsion. But due to tunneling, actually, enough of these atoms can tunnel through the repulsive Coulomb barrier, or sorry, enough of these particles can tunnel through the barrier so that they can actually fuse into helium nuclei, and that is what gives the mechanism for our sun to shine. Another interesting implication of the quantum nature of matter is Heisenberg's uncertainty principle. So Heisenberg says position and momentum of an atom cannot be determined simultaneously with absolute accuracy. If I know how fast an atom, for example, is moving, and I know that exactly, then where that atom is in space is completely indeterminate. And vice versa. If I exactly know its position, how fast or where it's traveling is indeterminate. This is a property of a wave. It's very hard to pin down the exact location of a wave without squeezing out uncertainty in all different directions. So these are, and in fact, the uncertainty of one of the properties multiplied by the uncertainty in another property has to be bigger than Planck's constant, a constant. So these are complementary properties. Position and momentum are complementary. Spin, atomic spin, for example, if I know its spin in one direction, there will be uncertainty in the knowledge of the spin in another direction. And energy and time are complementary properties. And I'm gonna, at least for now, leave that as a thought experiment for you all to figure out how do I have uncertainty in energy and time, and how that still works out for the universe that we have. Another fundamental of quantum mechanics is superposition. So this is most well understood by Schrodinger's thought experiment with the Schrodinger cat. The idea here is if I have a cat and I put it in a box, and inside that box I also put a poison that a ball will release and break the poison vial when a certain radioactive element decays. Close the box and wait for a half-life of the radioactive element. There's a 50-50 chance that it's either decayed or not, and the cat could be alive or dead. Classically, the cat's either alive or dead. But in the thought experiment and how it works in quantum mechanics is the cat is actually both alive and dead until you open the box and find a very relieved cat to be sitting there until you measure the system. This, again, is a very nice thought experiment that came up in 1935 between discussions between Schrodinger and Einstein. But this is actually how a so-called atom interferometer works. And that is shown here. If I have an atom and I shine a light pulse at this atom, with sufficient time, there's a 50-50 probability whether it gets a momentum kick or not. What actually happens is that atom goes into a superposition state and it travels both paths simultaneously, and we can recombine these atoms so that they interfere with themselves. And this is shown in this data from the German group where wave packets are separated, recombined, and they show a very nice interference pattern where they're interfering with themselves. And this is actually the root of a very powerful quantum sensor that I will talk a little bit more about in the future. Finally, entanglement is the similar to superposition, but if I have two particles that are, I don't know the state of an individual particle, but I know that they're tied together in some way so that the state of this particle is tied to the state of that particle. Again, quantum mechanics says that these two have a distant tie. They will both be in superposition states or multiple states until measured, and then you immediately know the state of one particle when you measure the state of the other, which is the root of quantum computing, which is a very emerging quantum technology in our world. This is the ability to make, or this uses qubits, quantum bits, which are highly entangled, so that you can set a process that goes through essentially massive parallel processing. The answer is not known. What state each qubit is in is not known until you measure the final answer, and it has the power to potentially speed up many equations. I think the actual impact of what quantum computing is going to have on our world is not yet known, but it seems like a very near-term technology that's going to be transformative for us. So that was a fair amount about quantum mechanics, but we're talking about the cold atom lab, right? Talking about cool atoms. So I'm going to now tell you, okay, very simplistically, when we're talking about cold atoms, a hot gas has fast particles that are relatively less dense. A cold gas has slower particles that are more dense. And for an ideal gas, they can follow these very simple laws of how the temperature relates to the speed, pressure, volume of a gas. Just for a handle on how fast or slow we're talking about, air molecules travel about 1,000 miles an hour on that order, which is much faster than humans or snails. But it's around the speed of a bullet, for example. ISS is booking along. It's traveling 17,000 miles an hour, and the fastest man-made satellite is actually at 400,000 miles an hour. When we're talking about cold atoms in Cal, these are traveling, we've cooled them down to temperatures on the order of 100 microns per second. We're getting down to sub-nanokelvin temperatures. Extremely cold, extremely slow atoms. So what does this mean for classical gas? They're cold, means they're slow. Louis de Broglie, about 100 years ago, said that, or defined a wavelength for an atom. And it's interesting when you look at this, wavelength of a substance is equal to Planck's constant divided by its mass times its speed. There's nothing in here that tells about what makes up this particle. It could be quarks, it could be planets and galaxies. It has a wavelength that's associated like this, related to a so-called wave packet. And this was critical for understanding how atoms work, how electrons do not decay down to the nucleus. It was found that the wavelength of the electrons about the nucleus have to have closed boundary conditions, and their wavelengths are on the order of 10 to the minus 10 meters for say, a hydrogen atom. Earth has a pretty small wavelength, 10 to the minus 65 meters. So it's very classical system. When you look at temperatures that we run into normally in the universe, anywhere from black body radiation all the way to center of the sun, for all of those, atoms and particles are on the sub-nanometer length scales, and that's why the universe that we know is generally classical. For the cold atom lab, the temperatures that we're cooling atoms down to, these sub-nanokelvin temperatures, the de Broglie wavelength of a single atom is hundreds of micrometers. It's around the size of a human hair, even. And so here, the wave-like nature of the atoms absolutely dominates the physics that we're studying in the system. And this is interesting. This property of cooling atoms down to extremely low temperatures, making the wavelength very large, allowed scientists to create a new state of matter in the lab that had been predicted by Einstein and Bose, but was not realized until the late 90s. And this new state of matter, in addition to solids, liquids, gases, and plasmas, is called a Bose-Einstein condensate. And this emerges when these atoms are cooled sufficiently so that the de Broglie wavelengths all overlap each other at high enough density. The system, because it's boson, actually collapses down into a single atomic state with a macroscopic wave function. Here are some nice pictures of a boson nova, where the Bose-Einstein condensates are collapsing in on themselves and exploding out due to their interactions. And so finally, this is a very nice map of quantum physics. I encourage you to check it out because it holds a lot of nice hints of everything that we've talked about and more, and how quantum plays from atomic physics through subatomic particles, all the way up to the many world theory. But I wanted to call out that quantum already does define our life and our standard of living. It brought us lasers, has a lot of impact to the medical industry. Superconductors is how we understand how the band theory of solids and how electronics work. And it's also being found that there are some quantum processes that are likely driving in biology too, from bird navigation, photosynthesis, sense of smell, etc. So it's very important for our life. We're studying cold atoms in space. We do that for three reasons. First of all, when you remove gravity, that allows us to get much, much colder temperatures. We essentially cold atoms by decompression cooling. We're releasing a trap. And on Earth, that gravity limits how much we can decompress the atoms, how much we can cool them by reducing the pressure. But in space, we can push that to its limit and have new cooling schemes. But also studying how two different gases of different masses interact on Earth, those separate due to gravitational sag. We can do that. Probably the biggest impact we have, though, is extended free fall. With these ultra cold gases, we're looking at them on seconds timescales, potentially tens of seconds to minutes in the future. And that already, to look at seconds timescales, you need tens of meters, 100-meter drop towers on the Earth. We can look at the same in a like a 1 centimeter cube apparatus. And finally, we're actually going to be developing sensors based on quantum technologies that will be useful for space science in the future. Highly precise clocks, highly precise gravity sensors to sense gravity, Earth, and planetary science. So that's why the Cold Atom Lab came about. It's a first of its kind multi-user facility to use a microgravity environment of the ISS for measurements with rubidium 87, potassium 41, and potassium 39 gases. These are all bosons. They can all produce Bose-Einstein condensates. This research is ongoing on the International Space Station, which is an amazing lab, especially when you think about what it took to get up there. It's about almost the size of a football field, 1 yard shy. Weighs 900,000 pounds, traveling 17,000 miles an hour around in Earth's orbit. It actually orbits every 90 minutes. And there's been almost 3,000 research investigations on the ISS from over 100 countries, including, of course, this physical sciences one here, which is my favorite because it has a symbol of the atom on it, which Cold Atom Lab is under. But a lot of it's been to study how do humans what is their progression? How can they live with in extended microgravity? And there have been some astronauts that have been on the ISS for a very long time, from Frank Rubio for 371 days, Christina Koch for 328, Jessica Meir for 205. And I call out those three astronauts because they all worked on Cold Atom Lab. Here's Christina Koch transporting one of our upgrades to install it. This is actually what it looks like for us when operations are going on to install things on the ISS, specifically in the Cold Atom Lab. We're in this room called the Earth Orbiting Missions Operations Center, or the EOMOC. And we have big screen TVs where the astronauts have cameras. We can see what they're doing in real time. We can talk to them. We can interact. It's a really great, engaging experience that I didn't expect that we'd have this ability to interact with the astronauts as they're doing operations on our instrument. But yeah, we do. It's been great. So how do we get atoms that cold? Start with alkali metal dispensers in the center of a vacuum system. This is a two-celled vacuum system, which is about an inch on its side. Heat these up to a couple hundred C and it makes a gas. One of the main and interesting cooling techniques that we have is laser cooling. Now, here is where we shine lasers in along all directions. And this is what I must admit brought me into the field, because I thought lasers heat up atoms. Makes no sense how you can cool to millikelvin temperatures with lasers. But what happens is that, yes, broad lasers heat things up, but lasers have a very precise frequency. And so you can tune them in a way so that wherever your atoms move, they're Doppler shifted into resonance with a laser that's counterpropagating the direction that they're coming. So no matter which direction an atom moves, it preferentially scatters light against its direction of motion. Gets a very tiny momentum kick, and it slows them down no matter how they're moving. It's almost like your atoms are being dropped in a vat of honey or something like that. It just molasses cools them down very quickly. Thereafter, after you reach millikelvin temperatures, the atoms are loaded into a trap. These are magnetic fields that form a trap and hold the atoms. And we just remove the hottest atoms in a process called evaporative cooling. Similar to how you cool down a cup of coffee or tea in the morning, blowing across the top of it. It removes the hottest atoms. Here we're using radio frequency fields, but just in the same way, remove the hot atoms, it rethermalizes to a colder temperature. And with that, you can get down to 10 to the minus 5 to 10 to the minus 8 Kelvin. This is tens of nanokelvin temperature. This is the process that actually allowed cooling down to a Bose-Einstein condensate in Eric Cornell's lab, Wolfgang Ketterle's lab, that led to their Nobel Prize. And then finally, we use decompression cooling, as I mentioned, similar to when you spray air out of a spray can. It gets very cold. It's because there's going from a high pressure to a low pressure environment. And we simply relax our traps or use some advanced techniques like release atoms and then recapture them to cool down to sub-nanokelvin temperatures. Now, most of the labs that I've worked in prior to coming to JPL looked like this. Very large labs. You have optics tables with lasers on all the sides, electronics from ceiling to floor, and a number of graduate students that are regularly attending the instrument to try to get the publishable data. Our instrument is a lot of the work before its launch in 2018 was to miniaturize and ruggedize and automate this instrument. So all of that those technologies for a state-of-the-art dual species BEC lab was reduced down to fit into an ISS express rack. So this is a quad locker about the size of a mini fridge on its side, and it contains the science module that has the vacuum system, collimators and mirrors to shine the light in for laser cooling and detection, all that inside magnetic shields with these heat exchangers for lasers, current drivers for our magnetic fields, and a PXI computer over here. And then at the very top of the top of the vacuum system is an atom chip, just like a chip that we run current through different traces, and that makes a trap for our atoms. This atom chip at the very top of the vacuum system is about the size of an eggshell, which I was worried about when I went to the first launch of this instrument, because launches are not quiet. Launches are not gentle things. I actually got to see the launch of this upgrade, and this is actually for a SpaceX launch, and we were a few miles away. I think 3 miles away from the viewing area. The sound was delayed when it got to us, but when the sound got to us, it set off car alarms. And at that point, I thought, this atom chip that's the size of an eggshell, I really hope that it's holding in there. But it did. It was great. It got up, installed on the ISS, and it worked fine. These same technologies we've actually taken back to our lab. So now something that used to be many optics tables head to floor are these very compact instruments that we use to simulate and vet our experiments both on in our Cal ground test bed and in the engineering test bed. This is essentially the engineering test bed is the Cal instrument that's spread out on a table. It's exact flight hardware that we used to run. Now, how we actually run these experiments is experiments are first developed by the principal investigators and then are fed at Jet Propulsion Lab into our missions operations and ground development teams, who send these tables, send these sequences to Marshall. Marshall then sends the command via the TDRS satellite network up to the ISS, and then we take pictures of our atoms. That's actually what you see down here. This is a data coming back where we've taken a picture of a Bose-Einstein condensate. Now, of course, as you take a picture of a Bose-Einstein condensate, it measures it. It's not this quantum system anymore, but we can see a very high density peak that corresponds to atoms that were all in this Bose-condensed state before the picture was taken. So pictures are sent back in real time back to the operators, to us in the EOMOC, and all this occurs with just seconds delay. We actually remote desktop into the computer on the ISS and command it directly, which is really amazing since it could be anywhere in orbit around the world. We regularly have outages. This is what a TDRS map looks like, where you have connection through various TDRS satellites, but then there's gaps sometimes where you don't know what's going on. And it's automated to the point. This is a picture of former NASA Administrator Bridenstine making a BEC, click and go in the EOMOC. When the pandemic hit, we actually had to adapt this because we didn't have access to the EOMOC or JPL for quite a while. So we were able to remote desktop in from our computers in our labs, and now we actually run the instrument from our computers from anywhere. We can run this. Okay, so one of the first results that we got was featured in this Nature article, which has my favorite cover of all time: an astronaut out there finding a Bose-Einstein condensate in space. It's just a great cover. But basically, what we presented is observation of Bose-Einstein condensates in Earth orbit, producing BECs, characterizing them, very reproducible BECs that we've made now very regularly since 2020. We also observed atoms stationary for about 1 second in this paper, and that was actually really great to see your atoms after you release. They're just sitting there for a second time scale, whereas on Earth, of course, they drop to the bottom of your vacuum system like a rock. Since that time, since 2018, we've been pursuing PI science. Science of Cal is really aimed for 3 big goals, like Ant-Man here, understanding the quantum realm. So we're studying quantum gases in space to try to understand their intrinsic properties and quantum matter in new regimes, ultra cold regimes, and without the perturbing force of gravity. But also to develop quantum technologies, atom interferometers, atomic clocks, and quantum matter itself can be a quantum technology. And so here we're really trying to exploit the sensitivity that you can achieve with quantum matter when you can observe it for very long times in free fall. And finally, utilize quantum computing. This is a version of Feynman's quantum simulator. These ultra cold atoms are highly controllable and very pure, so you can rearrange them to access the physics of more inaccessible systems, such as a very nice picture is shown with Rydberg atoms here, but there's been quantum matter has been proposed to study anywhere from quark matter up to neutron stars, black holes, etc. One of our PIs is Nathan Lundblad, studies the science of quantum bubbles. Apologies. And what we mean by that is he makes a shell-shaped trap and then is putting quantum matter inside that. And on the Earth, boson-side condensates will just drop to the bottom of a shell. But in microgravity can fill up. And there's a lot of new physics to be gained out of this, seeing how this matter with wave-like properties fills up a novel topology, how what happens when you stir it up. There's a lot of theory that can look into this and has and can be tested so that we know if we have a good understanding of what quantum matter, how that should behave in these various topologies. And here's actually a picture of inflated quantum bubbles that were in a recent Nature paper of his. Eric Cornell is one of the Nobel laureates for achieving the first boson-side condensate. He is one of our PIs to study the quantum few body physics, specifically the quantum three-body problem. If any of you have seen the three-body problem on Netflix, you know that the three-body problem is not simple. Quantum three-body problem is no simpler. But basically, this is trying to form three-body bound states, extremely weakly bound three-body bound states. And they're using the space environment to achieve ultra-low temperatures, which you need to make bigger and bigger and bigger three-body systems to test the theories, quantum few-body theories, better and better and better. Cass Sackett is studying the path to ultra-cold. So his research really focuses on how can we expand traps, how can we achieve extremely low temperatures of dual species gases, such as rubidium and potassium, and how can we manipulate them, move them around in optical tractor beams, which is a tool that we'll have in a near-term upgrade to the Cold Atom Lab. Nick Bigelow runs a consortium that is trying to mature atom interferometry, which again is this very precise force sensor or gravity sensor towards a test of Einstein's equivalence principle. So the idea here is that if we can make BECs of rubidium and potassium and drop them both, they should, Einstein says, fall at the same rate. This is the universality of free fall, one of the major tenets of all of our physics theories. If they don't, that would suggest if there's some small deviation in how those fall under the influence of gravity, that would suggest some new physics that could go beyond general relativity. And so they're doing initial experiments to try to bring us towards an eventual high precision test of Einstein's equivalence principle in a future system. But they actually used cooling techniques to achieve 52 picokelvin gases in space, which is extremely cold, coldest gases in space. And finally, my team are studying science of Feshbach molecules, these very large, weakly bound molecules, both to study ultra-cold molecular physics in a new regime, but also these might provide a new tool for atom interferometry or for precision tests overcoming such things as gravity gradients, because you can create these perfect molecules. I'd say perfect because they're essentially isotropic. And when you release them, they'll be overlapped with and very highly correlated systems. So yes, we've been operating since 2018, collected data from over 100,000 experimental runs for our 5 PI teams. And in addition to achieving Bose-Einstein condensates, dual species BECs we've achieved, cooling to 52 picokelvin. Quantum bubbles have been realized, as I showed in Nathan's publication. We have also demonstrated dual species atom interferometry, explored quantum mixtures, observed some immiscible behaviors between rubidium and potassium in space, and demonstrated the first use of AI as a quantum sensor in space. Now, very quickly, atom interferometry, I mentioned before, it's an analog of the Schrodinger cat. This is if we actually think about interferometry, optical interferometry is a very powerful tool. It's been used for a very, very long time in the sciences. And here, if you take laser light and split it on a beam splitter, depending on the environment that the laser perceives along both paths, it will come back and the light will interfere with itself and be read out on one of these two sensors, and can give you a very sensitive measurement of the environment of the lasers, or that's actually the technology that's at the heart of LIGO, the gigantic interferometer that has recently, that has detected black holes in spiral. We had a upgrade to the cold atom lab by adding a laser beam from the top that goes through this atom chip, a window in the atom chip at the top. We're able to implement atom interferometry. And this is the first measurements of AI that was seen where we varied the phase of this final laser pulse. And with that, which output port of the atoms come out in after they are recombined, varied in a sinusoidal way with the phase of the laser. Now, this is important because atom interferometers can be very sensitive to accelerations. In fact, going to space is important because the sensitivity of this phase output scales with the square of its free propagation time. And so you can go from hundreds of milliseconds to even seconds on Earth, up to tens of seconds and minutes in space. We will provide very, very sensitive measurements in the future. We also demonstrated a phase shear interferometer where two pulses were applied very short together, and you could write these fringes on each cloud itself. And this is important because this is a scheme that's going to be used in future precision atom interferometers, where you don't have to collect a lot of statistics to know exactly where you are on the phase. Each cloud actually gives you all the information that you need. And we also used the AI to sense the frequency of the laser itself. Just with atomic feedback, we could measure the frequency of the laser. So these were essentially first quantum sensor using atom interferometry in space. Specifically, we measured ISS vibrations by going to longer and longer times. And the ISS is not necessarily a quiet environment. You actually see the exercise bike right here, right next to our instruments. So where it can be a very noisy environment. We also demonstrated dual species Bose-Einstein condensates, shown here, rubidium and potassium gases, both in a BEC state, and simultaneous dual species atom interferometry with the same laser pulse. And this is important because even though the ISS is a noisy place and we very quickly can wash out our interference fringes with a single species measurement. By taking two species, they should react to vibrations identically. So if you take a correlation plot, you can remove all of that noise. And it's a way to get very high sensitivity measurements of differential forces on rubidium and potassium. Okay, so just looking forward to the future quickly. Atom interferometry, I think, is going to be a very important tool for the future, especially building on some of our initial demonstrations with Cal. PIs are already maturing. This is a AI is a precursor sensor for gravity gradiometry. The GRACE series of missions uses 2 satellites with laser ranging between them to map out the geo, basically the gravity signal from the Earth. And gravity signal from the Earth is very different from what the Earth optically looks like, because the different densities in water, land masses, what's below the surface of the Earth highly defines the actual gravity that you can measure out. Having these high precision gravity sensors are important for Earth and planetary sciences. But I mean, it's useful for measuring archaeology, things that can be under the ground, aquifers, changes to the landmass, etc. There's using atom interferometers in the future. We're planning to take this to the next level. There's a quantum gravity gradiometer mission that is being sort of scoped out at JPL, and this would use 2 atom interferometers that are separated in space so that you're looking at differential forces on two different atoms to look for gradiometry. In Cal, we demonstrated this splitting one cloud in 2 and then probing each and made a magnetic gradiometer. And these are some of the results that are soon to be published. This technology, I think, is evolving for Earth and planetary sciences, but also there are some big questions that we know about, things that we know we don't know. General relativity and quantum field theory are fundamentally incompatible. Even after 100 years, the 2 theories just do not work together for a number of paths, and there's a number of things that we don't know about them. So, for example, smoothness of spacetime and how that impacts the physics that we know. General relativity is based on a smooth spacetime. Quantum field theory, when you look at spacetime in much higher down around the Planck scale, it is not smooth at all. It's this bubbly mass of matter and antimatter that's being created and destroyed all the time. Do we need a quantum version of gravity to explain it, to understand what's going on, for the theories to come together? General relativity has a very nice and non-intuitive description of time, right? We know that especially there's gravitational redshifts, that space and time are tied together. But if you look at quantum theory, if you have an atom that can travel 2 paths of space-time in a superposition state, how does that hold together with the science? What actually will happen there? What is the gravitational field of a wave function? Many of these things are, as of yet, unknown. And these precision measurements that we're aiming for aim to look at answer some of these big questions and give new insights that might someday lead to new theories beyond general relativity, beyond quantum field theory. Also, there are big questions. It's from many, many different bits of evidence, either looking at distant galaxies, how they rotate, or lensing from distant galaxies. We know that there's a lot of stuff out there, but we don't know what it is. You can't see it. 95% of the universe appears to be invisible to us based on signatures of evolution and the way that different galactic different things move on galactic scales. And these are in the form of dark matter and dark energy. Atoms actually have a unique probe for both dark matter and dark energy. There are classes of both of these that may be able to be detected locally with ultra cold atoms, just because they can be ultra precise sensors and ultra dilute. And so these are also paths that we're aiming to explore in the near term to look for what is dark matter, what is dark energy in a complementary way. Cold Atom Lab, the future of where we are from here, Cold Atom Lab is currently operating. This follows from a MIAS sounding rocket from DLR that established the first cold atom experiments in space. There are ongoing Cal upgrades. Cal's expected to keep operating through 2027 when a follow-on joint NASA DLR mission called BCAL will launch to the International Space Station. But what the future is dependent on responses to the decadal survey. These are surveys that are to Congress that will come back and tell us where BPS and ISS should spend their money and how the program can move forward. We're expecting free flyers, hopefully Cal 2, things like that. So finally, this is a picture super atom, a pure BEC that we produced. We're always looking for people who are interested in getting involved with Cal. Visiting researchers, postdocs, graduate students, interns, please get a hold of me if you're interested. There's also opportunities for high school students, Drop Tower Challenge, school visits, or even share a story of how you think quantum mechanics works, because I'm always, I admit, I know how the equations work, but I don't know perfectly how it works. Quantum in culture. Finally, I just want to point out that if you haven't seen Constellation, Apple TV show, it's great. It's about a instrument called the Cold Atom Lab that ends up destroying the International Space Station when it finds some unique quantum phenomena it's not supposed to, and the lives of the astronauts associated. So yeah, it's a great watch. And here's also this interview with Paul Rudd and Ethan Elliott that I work with, where they talked about the quantum realm and some research with the Cold Atom Lab. And finally, this is a very nice video that is accessible to anyone on YouTube that explains in much simpler terms what we're doing with the Cold Atom Lab. And so with that, yeah, to summarize, we've operated on the ISS for over 6 years, collecting data for 5 PI teams. But we're really looking to answer to forge a path to answer some of the big questions in space. And some of the follow-ons for Cal and future high precision measurements, we really think we'll do that using BECs to answer what's the nature of quantum mechanics and what's the nature of hopefully dark matter, dark energy, and what's beyond. And so, oh yeah, and finally, this coming year is the International Year of Quantum Science and Technology from UNESCO. So keep your eyes out for a number of events related to that. And so, yes, with that, and on behalf of the Cold Atom Lab team at JPL and the PIs, thank you for watching.
Jason, that was wonderful. Full disclosure, that was a good walk down memory lane. My senior thesis was actually on the development of Bose-Einstein condensates.
Awesome. That is great.
Many years ago, so I couldn't do all that, but that was great. There was only one question in the chat, so we'll leave it. If anybody has questions to ask, please feel free to raise a hand. You can do so by, I think that's in the participant reactions, and you can just raise a hand. But Sharda had a question about the speed of Bose-Einstein condensates. And I think it was answered that they were microns per second, but if you could feel free to.
Yeah, so it all depends on their temperatures. When you get down to 100 picokelvin temperatures, then rubidium atoms are moving at they're expanding at about 100 microns per second. When you get hotter and hotter, most BECs formed on the ground are tens to hundreds of nanokelvins, and so those can be tens, hundreds of times faster that they're moving around.
So in the chat, can gravitational acceleration of hydrogen versus lead or uranium be measured?
So directly the atoms that we cool are sort of the first column of the periodic table. Yes, the work is going on to cool other species of atoms. They haven't cooled lead yet. Hydrogen is very, very tough to form, to cool down to Bose-Einstein condensates, but progress is ongoing there. I think that's the big trouble, is making ultra cold atoms out of these. But that does not mean that we can't have quantum versus classical um, tests where you could measure the acceleration of a Bose-Einstein condensate compared to a ball of lead in space, for example. See what you see.
Yeah. So Magda, I'd like to know, what are the limits of time measurement precision beyond the Heisenberg's uncertainty?
Measurements. So beyond Heisenberg uncertainty, that is a great question. So if you'll remember these complementary um, particle or complementary properties that we have, there's energy and time uncertainty. So I think that's the limitations that we know of right now, is as you're measuring timing of events more and more and more precisely, say a collision or something like that, anything that you can measure. If as you try to measure those with higher and higher and higher precision, um, the energy uncertainty is more and more and more unknown, and vice versa. To measure beyond Heisenberg uncertainty, then you're getting into physics beyond the standard model, which is great. It's something that we're always looking for. But yeah, those are things that we're also trying to explore with quantum mechanics, because we are able to achieve ultra cold systems, which means that we can control the energy very well, and trying to look for quantum classical transitions, and where Heisenberg uncertainty might come more into play.
I'm going to put my geology hat on. In terms of gravity measurements, how might the resolution of those measurements change based on your work?
Oh, okay. So gravity measurements. I'm going to talk about testing Einstein equivalence principle for fundamental physics. That has that's had a really great history to it. It's been one of the most tested principles, because everybody's trying to prove Einstein wrong. Um, so some of the I don't want to say earlier, but some of the most relevant measurements have been torsion pendulum on the Earth that can test gravity down to 13 digit points. There's recently also lunar ranging to the moon, can test how the Earth and the moon are falling with respect to each other and towards the sun to about that same precision. There's been a mission called Microscope that has recently measured down to about 15 digit points, the differential acceleration of two two species, titanium and one other. I can't remember exactly what. We are aiming in the future to match and exceed that. There are some mission concepts that are in proposal to test down to 18 digit points now. And the reason that people have been concentrating on that is because there are certain theories that predict violations to the equivalence principle in the 10 to the minus 12 to 21 level. Um, and I mean, even things like loop quantum gravity, string theory, things like that often predict violations of the equivalence principle. And so we're trying to really hit this regime that might look for new physics where contemporary theories are predicting there might be a violation, or to rule out these theories.
AC has another question. Absolute zero temp is impossible, but is there a theoretical lower limit above that?
Ah, I think this all comes from Heisenberg uncertainty principle. So the theoretical lower limit that I know of would be when your gases are the size of the universe or somehow are competing with the speed of light. Um, but yeah, I mean, there are definitely practical limitations to that. This, I think, is another test for quantum mechanics and how it could fall apart. There are limitations to that people are looking for. If I make a Bose-Einstein condensate, um, have it in space, try to go lower and lower and lower temperature, or just have it maintain this single wave-like system that's that's sorry, very pure, that's in phase. Will it dephase due to quantum gravity, due to quantum aspects of gravity itself, or any curvature deviation of space-time from smoothness? And that would set a limit for sure.
I think Sharda has a comment just to having a student who asked, can we go to negative Kelvin temps today and faster than the speed of light? I love those questions when the students bring them up. I think with Kelvin, you always we're so used to having negative temperatures, like you just want that one.
Yep, exactly. Negative Kelvin. So this is all about quantum simulation. There are ultra cold atom experiments that have gotten to negative temperatures. And basically, I think this comes from if you know what the distribution of atoms with a certain temperature distribution looks like, you can invert that to achieve negative temperatures. But that doesn't mean that it's traveling negative velocities and would break the speed of light or anything like that. It's just a simulation. Um, I'd love anything that can break the speed of light. I'd love to hear it. I don't have any theories off the top of my head, but but I'd love to hear it.
And AC is going to challenge you again. He says, can Bose-Einstein's diphase due to dark matter interactions?
Oh, sorry. So that was, can Bose-Einstein condensates see a dark matter interaction?
Yeah.
Yeah. So that, yeah, wasn't an absolute yes. That was, I understand the question. Um, that's so about a decade ago, there were some very smart theorists who looked at what could be dark matter, what could be dark energy, right? And one of the reasons that they proposed dark matter or dark energy could be a field that's all around us, but it might be that we don't see dark energy and its impacts on us because of screening. Something that maybe when you're around the Earth or something, it actually screens out the dark energy, so you'll only feel it in space or when you're away from matter. So they said screening could be a two-way game. You have screening from the Earth, say, and screening from your test mass. But if you use atoms, they're very low density. The screening from these atoms could be down by many, many, many orders of magnitude. And so, yes, there have been recent experiments to try to find these so-called chameleon dark energy candidates by using cold atoms that would be immune to certain screening phenomena that classical matter would be. And as of yet, they haven't seen anything, but they're marching down in precision and to keep looking for different candidates of dark energy that yeah, regular matter likely wouldn't be able to see.
Well, on that note, there are no other questions in the chat or no hands up, so I'd like to take a second and just say thank you for sharing your time with us. Been wonderful to have you. Hopefully we'll have you again. And for those who are with us, I believe we'll have the video of this posted probably within a few days. If you would like
Thank
to
you
view it
very
again.
much.
Thank you so much, Jason.
Thank you.
Have a wonderful evening.
You too, and thank you, everyone.